Okay, in number 17, they try to talk to you about a couple charged spheres here, and it's asking to draw the magnitude and direction of the electrostatic force exerted on A by B. So it's what's the force that's on A one way or the other. All right, if we look at B, we notice that this force is pointing away. So that means that these two particles, these two spheres must be repelling each other. Plus, both of these numbers are positive. So we need a repelling force. So that cuts out this, that cuts out this. Secondly, you can look at this one of two ways. You can look at this using the electrostatic force formula, where you have electrostatic force equals K Q1 Q2 over R squared. All right. Now, it doesn't matter which charge you put as Q1 and which you put as Q2. It doesn't matter if you put the 1 first and the 2 second, or the 2 first and the 1 second. Okay, either way you do it, the force is going to be the same. So you get the final answer. The force needs to be the same. So if this force is F, then this force also needs to be F. All right. The other way you could look at this is using Newton's third law, realizing that if you have two objects and there's a force between them, they need to have equal and opposite forces. So if this is F, that also needs to be F, and they're pointed in opposite directions. For number 18 over here, this one you have a positively charged particle moving between these two plates, and this one really no one should get this wrong. If you put a positive particle right here, it's going to get attracted to the negative and repelled from the positive. It is going to move down, and that is definitely towards the bottom of the page. Okay, that's an easy one. Just make sure you read that it's positive. For number 19, this one can be a little tricky if you don't know what you're doing. Look at what you're given, okay? This is a calculation question. It tells us that we're trying to find work, and it tells us that we know that we have a potential of 100 volts. So we know we have to deal with W, and we know we have to deal with V. All right, and we know W is our unknown, and volts, we have 100 of those. And so the question, right, we only have two things here, and generally we need more than two. So if we need to find some formula that relates these, we have a couple options. One you might notice is work equals PT, which also equals VI T. All right, and then you might be tempted to try to use this one that, oh, we know volts, but then you are going to end up making up a current and a time, and that's not a really good idea. So another one that you could use is V equals W over Q. All right, now this is promising, okay, except we don't really know Q, except we do know that we are dealing with a proton, and Q is charge, and the charge of a proton is something that we know, so we actually know that Q for a proton, that's one elementary charge. Uh-oh. What happened? We know that Q equals 1.6 times 10 to the negative, oh dear. Well, Q is 1.6 times 10 to the negative 19th coulombs. Okay. As I was saying, for number 19, you do know the charge on a proton, so you can use V equals W over Q, rearrange that W equals V times Q, and you can just multiply 100 times 1.6 times 10 to the negative 19th, and you will get answer choice number 2. All right. For number 20, this is another calculation question. So let's see what we have. All right, we are trying to find current. All right, current is I. All right, we know we have 240 coulombs. So that means Q equals 240 coulombs. And we know we have 2 minutes. Time equals 2.0 minutes. Now be careful. You know the time is 2.0 minutes, but you don't ever want to use minutes. So the time is actually going to be 120 seconds. So again, look on your reference table, and there's a really, really easy formula for this, where I is Q over T, so you get 240 coulombs over 120 seconds, and that's very easy, 2 amps. Boom, done. All right. Now, last one is talking about the, it's asking about the current through a resistor if you double resistance. If you remember what we did with the water bottles, when we were squeezing the water out of the water bottles, resistance is resisting current. So if you increase resistance, you're going to decrease current. All right, and your formula is just V equals I R. All right, if you increase, if this is going to be constant, okay, so it's constant potential with constant V. If this goes up, this has to go down. All right, and you make something with more resistance, the resistor, the current is going to decrease, and nothing is squared, everything is linear, so if one goes up by 2, the other goes down by 2, the current will be halved.